Okay, I lied. Let's get this done. Let's talk about a normal approximation of the binomial model. We're using the normal model to approximate a binomial result, okay? So, what happens, and ignore what this question says right here. We're going to change this in just a minute. What happens if I have a really large sample size, like I've got 10,000 kids? And of these 10,000 kids, because J and K have now apparently worked with the people from Men in Black, and they're not going to have kids, they're going to lay eggs. They're going to lay 10,000 eggs, and what's the probability that of those 10,000 eggs, let's say 2,600 are going to be type O. Okay? Now, we're going to use a normal model, and notice my typing here, we can use a normal model and our knowledge of normal probability. Normal probability means we're talking about Z to approximate probability, which I guess we're from the South, probability if we meet a few conditions. And these conditions are this: independence, which means you dance by yourself, because I can't type. Okay, independence. Okay, again, sample is less than 10% of the population. Then we have n times p has to be greater than 10. What is n times p? Let's talk about n times p for a second. N times p, n is the sample size times p, the probability of success. Say that I have a coin and I'm going to flip it 10 times. And I want to find how many heads am I going to get? Well, I would take that sample of 10, multiply it by the probability of 0.5, and say, oh, you know what, I should expect to get 5 successes. And that's what this is. This is the sample size times the probability of success. And what this value is the expected number of successes. So what this is saying is that the expected number of successes has to be greater than 10. We'll talk about why in just a second. So if n times p is probability of success times the sample size is the expected number of successes, that means that n times 1 minus p, which happens to be failure, is going to be the expected number of failures. And that also has to be greater than 10. Now, why do they have to be greater than 10? Because think about what we're doing here. N times p is, if I expect to get 10, expected value is also known as the mean. So talk about your normal curve here. Here's my mean right here. I need to have more than 10 successes and more than 10 failures to kind of guarantee or show that I have the chance of having a relatively normal distribution. Okay? So, with this, okay, the mean, n times p, oh, we just said that, the expected value, n times p, two things when I'm talking about z. Z is equal to x sub I minus the mean over the standard deviation. So, z is equal to x sub I minus the mean over the standard deviation. What's the mean? Expected value, n times p. What's the standard deviation? That's a really good question. Well, it turns out the standard deviation is going to be the square root of n times p times 1 minus p. Whole lot happening here. So let's take these values and do this. Let's insert a new page after this. No, let's go to page. Let's go to page. Insert new page. Okay, so here's what we're going to do. Let's find the probability that we are going to have more than 2,600 kids with type O blood. Now, our sample size is 10,000. Our probability for success is 0.25. Z is equal to x sub I minus the mean, which is n times p, over the standard deviation, which is the square root of n times p times 1 minus p. Let's fill the values in that we know. 2,600 is our value of interest, so we'll say this: 2,600 minus the mean. The mean is n times p. 10,000 times 0.25, 2,500, over the square root of 10,000 times, I don't know why that comma's there, 10,000 times 0.25 times 1 minus p, which is 0.75. All right, let's figure what this is. Get out of here. Clear? So, numerator's 100. So, I'm going to have 100 divided by square root 10,000 times 0.25 times 0.75. And we get a z-score. Nope. That's not right, because you know what, I had 1,000 here. Let's try it again. 100. Delete. 100 divided by second square root 10, 1, 2, 3 times 0.25 times 0.75 equals 2.31 to 2 decimal places. So this is equal to 2.31. Okay, so what does that mean? Let's talk about the normal curve. Page, insert, new page. Here's my normal curve. 2.31. I want to find the area to the right of that because I want an x to be greater than. Okay, it's like the IQ question. What's the probability of having an IQ above 115? So we turned it into a z-score. I'm doing the same thing here. So I could go to the table. I go to the table, I find 2.31. Table gives me area to the left, and I subtract from 1. But here's what we're going to do. We're going to use the calculator to do this part for us. Because the calculator can do this, because it has a distribution. This is a distribution. It's a normal distribution. And we'll go to the distribution menu and say, oh look, there's normal. Well, normal PDF is exactly, and normal CDF is cumulative. And the z-table is cumulative. The normal curve starts at 0 and goes all the way up to 1. So we're going to use normal CDF. So we go to normal CDF because we haven't done this yet. And we find that the syntax for normal CDF is lower boundary, comma, upper boundary. And we're going to put those in Z. Okay? So, our lower boundary, because we're starting at 2.31, is easy. What's the upper boundary? Well, where does this go to? Well, the answer is it goes to infinity. So what we need is we need a z-score to represent infinity. It turns out that you could use probably anything above 9 and we're going to get the same answer. But because later on we need it to be 999, we're going to say infinity is 999. And what we get is we get a probability of 0.0104. And we're going to end it right there, 4 decimal places, because that's what the table would give us. 0.0104. Okay, what would we do, however? Say, for example, instead of being greater than 2600, we wanted less than 2600. We wanted this area over here. What would we do? Well, we could use the table, obviously. But if we're talking about using the calculator, what we're going to do is we're going to go from our lower boundary to our upper boundary, normal CDF, lower boundary, comma, upper boundary, and we think, okay, we're here at 2.31, but we're going to cross through 0, and then we're going to go down here to where? To negative infinity. What's negative infinity going to be? Negative 999. So, second, distribution, normal CDF. From lower boundary, negative 999, comma, up to 2.31, our upper boundary, and we get 0.99955, which is 0.98955, which is 0.9896 to 4 decimal places, which happens to be the complement of this exactly. So that's exactly what we expected to get. Okay, so next time, that's it for actually the notes for the chapter, because we've done the normal curve. Next time, what we're going to do, we're going to work problems out of the book, and we're going to see the probability distribution, we're going to see the geometric distribution, we're going to see the binomial distribution, what you have to write, and then we're going to also do this as a normal curve as well. It looks like it's a lot, and it is, but we will make it work, okay? So there you go. Problems next time. This will all hopefully clear up as we go.